So now we're talking about three types of solutions: neutral, acidic, and basic. And these are the actual definitions of these solutions. You may have heard different ones. An acidic solution is one for which the hydronium concentration is greater than the hydroxide. Now remember, hydronium is the species you associate with something being an acid. Hydroxide is the species that you associate with being a base. Think of the Arrhenius definitions, right? And for a basic solution, it is the opposite. The hydroxide concentration is greater. And the actual true definition of a neutral solution is that the concentration of hydronium and hydroxide actually are equal, no matter what those numbers are. So look at the table 2 down there. And so these are solutions for which we are adding this HOCl to water. Now the first solution we have added none. And then after that, we have added 0.3 moles, 0.75 moles, and 0.1 moles respectively of these. So are these solutions either acidic, basic, or neutral? So just take a look. Okay, the first one, they're actually equal, right? So this is neutral. And note that number, 1 times 10 to the negative 7. Now in the second solution, we have more acid than more hydronium than hydroxide, so this is going to be acidic. Same thing here, and same thing here. So what does this tell you? This tells you that HOCl is a weak acid, and it's actually it's called hypochlorous acid, and it is the active ingredient in bleach, or one way to make bleach. Now, let us continue to look at, no, actually, we will continue to look at our HOCl solution here, hypochlorous acid. And what I would have you do, again, if we were all in the same room together, is have you using these numbers. I would ask you which, if any, happen to be constant. The sum of the hydronium and hydroxide concentration, the quotient of the hydronium and hydroxide concentration, the difference between the hydronium and hydroxide concentration, or their product. Now hopefully there would have been at least 4 groups, and I would assign each expression to a group, and they would kind of crunch the numbers for all 4 of these solutions and report back on the board. And what would happen is you would say that that one's not constant, that one's not constant, that one's not constant, but for the 4th expression, it is constant. And you might ask yourself, why? Go ahead, ask yourself why. All right, so this is also something that we, I think, came across in an earlier lesson. Acid or base behavior is sort of a relative thing. And there are some compounds, like water, that are actually quite happy acting either as an acid or a base. And more or less, it depends on what else is around. In the presence of a stronger acid, water is perfectly happy acting as a base. And in the presence of a stronger base, water is perfectly happy acting as an acid. So that might lead you to the question, what about if there is nothing else around? So it turns out that water, among other compounds, can actually transfer a proton to itself. Not actually to itself, but to another water molecule. And so let's just follow the path here. And that we're hopping a proton from one water molecule to another. So the water molecule that donated the proton ends up as hydroxide here, and the water molecule that accepted the proton ends up as the hydronium. Now, this is called the autoionization of water, so that's the title here, and is considered to be a sufficiently important process that its equilibrium constant is given its own symbol or subscript. This is called Kw, so W for water. And what's the expression for it? Well, concentration of the products raised to the power of their coefficients, so H3O plus and OH minus, divided by the concentration of the reactants, but the reactants are a pure liquid, which means they don't show up in an equilibrium constant expression because their concentrations do not change. So this is it. The product of the hydronium concentration and the hydroxide concentration. And at 25 degrees Celsius, the numerical value of this is 1 times 10 to the negative 14. So let's do a quick exercise here. So given that, what is the concentration of these guys in a neutral solution, right? So remember that neutral solution means that the hydronium concentration and the hydroxide concentrations are exactly the same. So we could say that both of them are equal to x. So we've got x squared equals 1 times 10 to the negative 14, which means that x, which would be equal to the hydronium concentration and the hydroxide concentration in a neutral solution, is equal to the square root of 1 times 10 to the negative 14, which is 1 times 10 to the negative 7. Remember the concentrations from the table a couple slides back. That was the concentration of these two in a neutral solution. And this, in fact, is the only concentration where those two can be equal. Because this expression tells you that they're related. That their product has to be 1 times 10 to the negative 14. So, and the way that multiplication works is that if one increases, the other has to decrease if the product is to remain the same. So the only time their concentrations can be the same is this magic number of 1 times 10 to the negative 7. If the concentration of hydronium is larger than 1 times 10 to the negative 7, that means that the hydroxide concentration must be lower than 1 times 10 to the negative 7, and vice versa. So the very, very, very important take-home lesson here is that in aqueous solutions, because of this autoionization equilibrium, the concentrations of hydronium and hydroxide are not independent of each other. So if you know one, you know the other, because their product is always this number right here. And remember, this concentration, this statement, is only applies. So this is the only time, this is the only concentration where you can have the two of them are exactly the same. If the concentration, any other concentrations, they must be different, but they can be calculated from this relationship right here. And that is a very, very important thing to know. You know the hydronium concentration, you know the hydroxide concentration, and vice versa. Okay, next up, pH. So pH is something you might have heard, and it is merely another way of expressing hydronium concentration. And it is a subset of a very common, to some people, mathematical thing called a P function. What's a P function? Well, whoops. There we go. Sorry about the order here. Basically, the P function of a thing is merely the negative base 10 log of the thing. So in particular, pH is equal to the negative base 10 log of the hydronium ion concentration. Likewise, but a bit less common, there's something called a POH, which is merely the negative base 10 log of the hydroxide concentration of something. But usually more and more you use pH. Basically, so it's a logarithmic scale. This is a base 10 log, and let me give you a calculator warning here that the ln key is not the same as the log key. Again, this is, log is reserved for the base 10 logs. Ln key is referred for the base E of logs. So you remember E from the kinetics units. So a couple quick examples. Basically, I want to do this so that you are aware of how this functions on your calculator, because again, everyone's a little bit different. And so let's presume a hydronium concentration of 3.7 times 10 to the negative 5 molar. The pH of the solution would simply be the negative base 10 log of 3.7 times 10 to the negative 5th. And if you're using your calculator properly, this should return 4.43, and that's the right number of sig figs. And how does it go in the other direction? So I will scribble this on the side here, that so let's say we had a solution with a pH of 2.81. So the way that you undo this, so generically the hydronium concentration is going to be equal to 10 raised to the negative power of what the pH is. So 10 to the negative 2.81 power. So this, you're going to look for a key on your calculator that's probably labeled as 10 to the x. And that should return a value of 1.5 times 10 to the negative 3. So make sure you can replicate those calculations so that you know that you're using your calculator correctly, and that's pH.